So welcome back, everyone. So let's get started with the lecture. So sorry, I was a little bit late getting started today. I was printing out homework 5. So if you're in the classroom and you haven't picked up homework 5, I've got some printouts up here. We can do it after the lecture. If you're watching online and have had trouble printing out the homeworks, as some of you have told me, I've been printing them out and bringing them into the lecture, so they are available if you're having trouble printing them. So we're going to talk today about covariance and correlation, which is extension. We're still talking about joint random variables, but now we're going to have these summary kind of values, properties of them about how they vary with each other, which is what these two terms mean, and we'll see them more formally defined in the lecture. We are kind of wrapping up the section on probability. And we're getting, so that means quiz 8 is today. It's going to be so a little bit on kind of joint random variables and the covariance correlation, and I think I'm hopefully going to get to show some examples of the bivariate normal or the Gaussian distribution in 2 dimensions in R today. If we can do that, we will wrap up the probability section. Kind of getting antsy that we've been telling you all this kind of mathematical stuff, and you're asking me, why is this useful? But I haven't been able to show you any actual data, and then we do stuff on data. That's because the probability part doesn't talk about data yet. When we get to statistics, we'll start talking about how to think about data on here, which is not described by probability distribution, but described by some observations. Okay, and then we want to use the ideas from probability to understand those observations. So I'm eager to get to that. So I'm hoping we'll get to that on Tuesday, and I can shift the schedule up yet. But this is what I kind of had at the start of the semester. So we'll kind of, unless we can finish everything, we'll stick something closer to this. So a couple other notes. Let's see. Homework 4 should basically be turned in. You can still turn it in late by the end of today. Hopefully everyone's trying to keep up and turn everything in. And if you have trouble formatting, it sounds like the vast majority of people are figured out how to format putting plots in the PDF, and everything's working fine, but I keep getting kind of a different handful of people who have trouble with this. If you email us for help on this, or you come to us, we will provide you help. We'll probably actually, if you show us something formatted wrong, we'll probably give you a little slack and turning it in to help you format correctly. But we will expect it to be turned in formatted so the plots are embedded onto the PDF, so we can grade it easily on Gradescope. Well, again, any questions or concern about that, please reach out to us. We'll help you with that. Most people have been able to do this fine, it seems like, but there's always a couple people with lots of questions, and that's okay if you haven't done this before. Homework 3 grades came out, and we have been there were some different interpretations of the questions. We have been revising those in Gradescope based on regrade requests and various things, and I think it was it question 2. Question with the equations and the R code, and whether the R code counted as an equation. So we made the deduction smaller. Then I went and talked to some TAs, and some TAs were confused about this, and I told some students that something related to maybe that could serve as an equation. So we're kind of still revising this. I think it's mostly all set. This is 2 consequences. The grades have improved for the class, and I think they're reflective of your knowledge, which is good. And 2, the grades in Gradescope are a little bit updated from those in Canvas. Porting grades from Gradescope to Canvas is mostly automatic, but not entirely. So we don't do it every So 5 minutes, we're going to do it kind of once when we think we've pretty much resolved everything about the grades. So we'll probably do that soon, but if you see some delays between the grades and Gradescope and on Canvas, that's why the Gradescope ones are more up to date. Yeah. So, okay, great. So I got a lot of questions about those things, so just kind of addressing those for everyone. Homework 5 is out. You need a charger? Yeah, right there. Yeah, great. Homework 5 is out. It's linked off of here. It's on, kind of it asks you to do a bunch of things with these, joint random variables, calculating some stuff. Again, mostly extensions of what you've already done. There's kind of one long question on discrete ones, one long one on continuous random variables, and then at the end you'll calculate some covariance and correlation. Okay, so should be kind of working through a bunch of calculation, but we should have all, after today's lecture, we should have all the material we need for that, so you guys can get started on, again, your printouts up front here you can pick up after class. So, okay, any questions on where we are in the semester, in those details? All right, so great. So okay, quiz 8 will be today, which means it'll open at 5 p.m. At about 15 minutes left, I'll stop and make sure we review everything that'll be on quiz 8. Okay, let's get on to the lecture. Okay. All right, we're talking about covariance and correlation. The first one here, so covariance, really think of this as variance, right? If you remember, variance was something we talked about for random variables already. It's kind of the expected squared deviation from the mean, and we have to deal with expectation, right? So I'm going to start by just talking about actually expectation for joint random variables. For joint random variables. All right, so again, we have these joint random variables, x and y. Okay, and so we're going to have two properties about them. One, we're going to have a joint, so PDF, f of x, y, and I'll probably again use a shorthand, just f of xy. Okay, so this is the thing that you integrate to get the probability distribution, or if it's discrete, you add up over the discrete possible values, right, to get the probability of certain kind of subsets of these values. But often when you look at this, you often get a, I want to talk about expectation for these joint random variables. And expectation, at least in this class, we'll think about this being a single scalar value. Okay, so when I have two random variables, I can take the expectation of x, I can take that of y, but I often want to take it of a function that combines x and y together, like x plus y, right? And also a function on random variables, and this will be g of x and y, and you can think of this as resulting in a new random variable z. Okay, so an example of this might be something like 3x plus 2 xy squared. Okay, so that's this is a function, so that this could be g of x y equals here equals this value, and this will be a new random variable z. Okay, Okay, so because to compute an expectation, we only want a single value, and we don't know how to combine kind of, so if we were to write just, so the expectation, remember, the expectation of x is equal to the integral of x to minus infinity to infinity of x times f of x dx, right? And so what was kind of, what I needed here was this value x to be multiplied, right? The value that the random variable took times the likelihood, or kind of like the probability, right? That the infinitesimal probability, it took that value. But when I have x and y, I don't know what to do in that place, right? So I have to combine them somehow. I could add them together, I can multiply them. And in general, I put some function there, some function g is going to how I'm, so combine them together. So if I want expectation, I need some property of both of them. And so I need this because the covariance will be one of these, so functions. Okay, so now I can define expectation, but it needs to be with respect to both this f function, which is the PDF, the joint PDF, and the g function, which tells me how to combine them. Okay, so now I can say that the expectation of the random variable z, which is the expectation of g of xy, okay? So this will now look kind of like we expect. This will be an integral over x and integral over y out of all the possible values. So this goes from minus infinity to infinity, okay? Of the value that z takes, right, which is g of x and y, okay? But then I need to know the probability distribution. I'm integrating over all values x and y. That's described still by f, right? So then this is, I did dy dx here. Okay, so this will be the expectation of this. So this was, you probably needed this for one of the homework questions. And I kind of, people started asking me questions right at the deadline. And I realized that while this property for one random variable was in the material around expectation, we didn't really cover it as explicitly. So that probably made that problem a little bit more difficult than it could have been. But you can do this with just one random variables with this function g as well. Okay. I can also do this for discrete, right? In discrete, the integral becomes a sum, right? Over all possible values. Okay. All right, so why is this the right thing to do? Well, so the kind of the tricky thing is we could say, well, there's one random variable z, right? But it's hard to kind of figure out what is the, we don't necessarily know what is the PDF of z right away. We could try and solve for it, but we do know we're often given the PDFs of x and y. Those are often so given to us. So this allows us to plug everything together without, we have to solve this equation, but we don't have to do some sort of manipulation before we solve it. All right, so I'm going to give a little intuition on why this is true, and I'm kind of illustrate why linearity of expectation. I'm going to derive linearity of expectation from this equation. All right, let's write out the, so let's revisit linearity of expectation. And now we'll go through this with two random variables. So we're going to have our function in this case is going to be g of xy is just going to be rx plus s, so sy. It's going to be a linear function. This is basically up to up to adding constants onto here, which is very straightforward. This is about as complicated as a linear function can be. You can have other linear terms, but you can always simplify them into this form. This captures kind of all the complexity. There are constant coefficients, right? These are constants. R and S are constants, and X and Y are the variables here, okay? And so we're gonna want to calculate the expectation of now R X plus S Y here, right? So this is our function of X and Y. And I'm going to kind of show you that I can decompose this into kind of just looking at the expectation of X and Y, adding them together and multiplying them by the coefficients, right? So you'll see what the answer is as we get to it. Okay, but first let me write out again now the discrete version of what this expectation means. So we're gonna iterate over all values of X and all values of Y and indexed by I and J. Okay, so this will be R times the value AI plus S times the value BJ times the probability that X is equal to AI and Y is equal to BJ, right? So this is a joint probability now. So assume I have access to the joint probability. This is how I write out the expectation of this function, in this case, a linear function of these two random variables, so X and Y. I iterate, I sum over all possible values they both can take, multiply that function of their values times the probability that they take on that value. Okay, or at least that the variables X and Y take on that value. So again, if you remember, like if we roll two dice and we add them up, there might be multiple ways, for instance, to get a particular value in here. Like the value 7, the sum of two dice. There are kind of 6 different ways you can get the value 7, but I don't want to have to calculate that joint PDF. I just want to figure out, well, I know each combination, a 2 and on the first die and a 5 on the second one, each of those is 1/6. And so the probability on the right here will always be 1 out of 36 in that case, right? So this is a little bit easier to work with. Okay, so now, so I want to derive the linearity of expectation. So let's how do we do that? Well, I'm multiplying that probability, which is kind of a fixed value that's known, times these quantities. So I'm going to factor that through. Okay, so I can pull out I can do things like I can pull out this coefficient and this coefficient and so forth. Okay, so let me do a first step here. I'm going to move this R in front, and I'm only going to sum over the terms of A. Well, I'm going to decompose this into 2 terms based on the R part, that kind of the RX part and the SY part, right? So this term will only be over A, and I'm going to push through this probability X equal to AI, Y is equal to BJ. Okay, now I'm going to add to that this term. I'm going to pull the S in front, see the BJ here, and again, this probability X equals AI, Y equals BJ. Okay, so that just kind of use the linearity of this kind of expression to kind of factor this out. Okay. Now I can, for the first term, I can take R and sum over the values I that AI that X is taking on, but I'm going to factor out this AI because that AI does not depend on J. Okay, so now I can say, well, this is sum over J times the probability X is equal to AI, Y is equal to BJ, right? And I can do the same thing over here. S sum over J, Bj. Now I'm gonna push in the I here, probability X equals AI, Y equals Bj. Okay. Okay, what's interesting is these terms are now marginalizing over J and then over or over the values of Y. This is so marginalizing over Y, and this is marginalizing over X, right? So I'm summing all possible values that Y can take over the first term and then over X. So what this does is it says, well, the first term underlined in green there does not care about what value Y takes in the probability. It's summing up over all values it can take. So I can kind of get rid of the probabilistic aspect of Y, right? So AI, and now this is just the probability of X equals AI here, right? It didn't matter. I marginalize over Y, and I do the same thing over here. S times sum over J, Bj, and then this is just the probability of Y equals Bj. Okay. Okay, so I've marginalized out those quantities. And now, if I look at this term here, this is just the expected value of X, right? I'm summing over all possible values A can take, and I'm multiplying that value A times the probability X takes that A. That's exactly expected value of X, and this is exactly the expected value of Y. Right, so I have equals R expected value of X plus S times the expected value of Y. Okay, great. So I've derived this equation, right, which is the X is the linearity of expectation, which we had talked about earlier. Now that we kind of know a little bit more about joint random variables, if I have two of these random variables and I have a kind of equation of them that's a linear equation, I can factor out the coefficients and I can factor out the expectations of the individual things. Okay, so this is how we get this linearity of expectation. Okay, cool. Right, so hopefully you already knew this was true, but now you see a little bit about why this is true. And hopefully it helps give a little bit more intuition about this top equation, what this top equation is doing, where if you have a function of two random variables, why the expectation of that function is written in this way. All right, great. You got the picture up there. You'll have the picture before I post them online. Awesome. Okay. All right. So now that we have this revisited machinery a little bit, we can get into kind of the core, most important topic of this lecture, is covariance. Okay, this is for two random variables, X, Y. It measures how they covary with each other. Okay, it measures how X and Y vary. As X gets larger, what can we say about Y? Right? Does it also tend to get larger, or does it tend to get smaller? Does it stay about the same? This is what this kind of quantity measures. It's a quantity like expectation, like variance, but it depends on two random variables now. Okay, and let me just get to it. We're going to call the covariance of X and Y like variance, but we'll use COV to represent this. Taking two random variables, okay, and it's going to return the expectation of x minus the expected value of x times y, x minus the expected value of x times y minus the expected value of y. Okay, so this is the expression. It should look like the variance. What was, remembers what the expression for variance was? Here? Yeah, right. Yeah. So you have to be careful where you put the parentheses. Yep, but variance of x is equal to the expectation of x minus the expectation of x, and this whole quantity is squared. Okay, so that looks kind of like this, right? We have we have x minus the expectation of x. That's the same in both of them. In the variance, it's just that term squared. But now we have two terms, and the y looks just like that, right? We've looked at the difference of y from its expected value, and we've multiplied that by x, right? So if we were to call, we should be able to immediately see that the covariance of x is equal to what? What is the covariance of x? Yeah, this is exactly the same thing as the variance of x, right? Because x minus x is the first term, and the y is now an x. So it's, again, multiplied by an x minus expected value of x, right? And so that is exactly the definition of the variance here, okay? So it's kind of a version of the variance that takes in two random variables and instead of just one of them, right? So, okay. All right, so what does the variance tell us? All right, so there are kind of a couple kind of points that this will tell us. If covariance of x and y is positive, so it's greater than 0, then this says that that x and y tend to vary in the same direction. Okay, then as x gets so larger, y tends to also. And by tends, I mean like in expectation, right? This is based on expectation, right? So if x gets larger, the expected value of y should increase. Okay, so so we can think of this kind of like a plot, and we'll actually plot pictures of this later if we keep going, and think of like a density plot. This will be like an ISO level plot, and we'll plot things like this. Okay, and so think of the densest layer where you have the highest PDF, right? So this would be like the f of x, y, right? This is the PDF, and this is the largest value. So this is so the largest value. This is kind of how to read this. Have you seen these contour plots or isolevel plots before? Is this kind of a new way of, or does this kind of look familiar? Like if you look at like topography of Utah, where you see the mountains, there's an option in like, so Google Maps, it draws these lines where everything is at the same elevation. And right, so the big Wasatch Mountains are higher up in these things, right? So we've got a simple one mountain in the middle of a plain, right? So maybe like kind of like the Ochre Mountains, a little bit, okay? Or maybe Antelope Island in the Salt Lake, right? So it's kind of coming out of a plain. That's where the peak is, and then it kind of is deviating, okay? And we want to think about what happens if we look at, this is kind of the values of x, and these are the values of y. And we can think of this particular value of x1, and let's look at the conditional probability, right? This is right here is f of y for the value of y given that x is equal to x1, right? So the conditional probability is the restriction, is the probability that y takes, right? So that appears on the y-axis here, given that the x value is here. And we could say, and the last lecture, we talked about something like if we kind of we calculated the expectation of y given x equal x1, right? So we can calculate the expectation of this, and that might be about right here, right? So this would be the expectation of y given x equals x1. Okay, but if we look at a larger value of y, let's look at a larger value of x, x2 is increasing. In this plot, what do we think the value of y? Is it also going to tend to increase or decrease or what? Well, you look at the expected value of y restricted that x is equal to x2. Yeah, I'm just telling you by looking at this picture. I haven't, yeah, the covariance turns out to be positive here, yeah, right? But looking at this picture, I look at the expected value. It's probably about here now, right? So this is now the expected value of y given x is equal to x2, right? And so this is larger, right? This has increased, and we've also increased x1 to x2, right? So if this is generally the case, kind of on average over all the pairs of values of x, as x1 increases to x2, does the expected value of y, given that value of x2 is what we take, does that also increase? And that's the case here. As the x value increases, the y value, corresponding y value also tends to increase. And this is kind of intuitively what the covariance positive, so covariance, kind of the picture you should have in your head. This corresponds to positive, so covariance between x and y. Okay, so as the x value increases, the y value also tends to increase. Right? Does that kind of make sense from this picture? We'll try in R see other ways of plotting this a bit later. Yeah. We haven't defined correlation yet, so just hold on. Yeah, great. All right, yeah, correlation will be related to this. Okay. Okay, so what if the covariance between x and y is less than 0? Is that possible? What would the covariance of x and y what would it, do you think that would mean if it was less than 0? Is that nonsensical, or does that have any intuitive meaning? Yeah. Yeah. Right, yeah, so x minus expected value of x and y minus expected value of y. Right, so this could be possible, and it helps to look at this equation, right? Let's look at these two values. Can this value be some negative? Yeah, in fact, about half the time it's negative, right? Because I'm subtracting off the expected value of x, right? So it's not the median would be the exactly half the time, but it's roughly half the time the value of x is going to be, so is the value of that first term is negative, and same with this term, right? With variance, even if that term was negative, well, we squared it, so it became positive. So variance is always positive, right? But covariance can be negative here because we could have x as positive and y is negative, or so vice versa. Okay, so this can be negative, that's fine. Okay. So it's fine if it's negative, and that so it's negative. So corresponds when so x is greater than the mean, but y is less than the mean, or x is less than the mean, but y is greater than the mean. All right, let's draw a two-dimensional picture again. This is x, this is y, right? This is expected value of x. It's somewhere on here. Let me just choose a value, expected value of y. Okay, so I can say, I can write this point here for expected value of x and for y right there. Okay, so this covariance is negative when I choose values where, say, x is greater than the mean, right? So it's over in this half, but y is less than the mean, so it's down here. So those both happen in this region, right? X is greater than the mean, but y is less than the mean, or up here. That would also be fine. X is less than the mean, y is greater than the mean. Okay, so now if I have a distribution that the expected value, I'm more likely in the pink regions than not in the pink regions, that would be kind of isolevels that look like this, right? So most of the mass is in the pink regions and less of it is in the non-pink regions here. Okay, so that corresponds with plots that kind of look like this. This would be a negative, so covariance. All right, this makes sense. Okay, so covariance is a score you can compute about random variables that quickly tells you, are they kind of, do they both increase together, or when one increases, does the other tend to increase? Does the other tend to decrease? There's one other case. What if covariance is 0? Right? Of xy equals 0. What if covariance of xy equals 0? Yeah. Oh, doesn't mean that the expected value of x equals that of y? No, these could be even different. So units, they're not really comparable, right? You have x here, you have y here. You know, this could be measured in inches, and this could be measured in kind of like like seconds, right? One's measuring time, the other is measuring length. That would be totally fine. That makes sense to kind of have joint random variables measuring these things. It doesn't even make sense to, you know, even so compare these quantities. Okay, so it's not quite that. That's not quite the right thing, but a good thought. Yeah, there is some tricky stuff that I want to mention about what does it say about these random variables and what does it not quite say. It kind of means that it should be kind of, remember we drew this plot. These are the expected value of both. And we said, well, if it was negative covariance, it was more likely in this quadrant or in this quadrant. And if it's positive covariance, it's more likely in this quadrant or in this quadrant. And if it is exactly 0 or very close to 0, then this should be somehow balanced, right? It should be somehow about equal amount of the pink and the green, right? So that should be something probably like this. As I get more density, it kind of goes out somewhat evenly. This should be kind of the picture you have in your mind. Okay, so that's kind of, it's not slanted going up or it's not slanted going down. It's kind of even. Okay. Okay. So all right. So you can even say that so if X and Y are independent, then we have to have the covariance of X and Y is equal to 0. So if X and Y, like if you go back to this picture, these random variables, when I get a distribution that looks like this, I get kind of the same density no matter where I cut it. It might be lower, kind of the height might be lower, but they're kind of going to be independent of each other. You could have another one that looked like this, right, where I got squares. No, this is not, that one doesn't work, right? But if it was a single uniform distribution over a square, this would also be independent, right? So if I said it was uniform over, say, 0.2 to 1 squared, right? So if it's uniform over that box, well, then that's also going to make them to be independent of each other. And that kind of is, if that's put so it's, and if that's centered on the mean, right, which it should be if it's uniform over the box, well, then it should have even amounts of the green and the purple as well. Okay, so these are kind of examples of covariance of 0 and the random variables being independent of each other. But if the covariance is equal to 0, it might not mean that X and Y are so independent. Okay, so we don't have the reverse. Okay, so it might not be that they're independent. There are situations, and I plan to show you one at the end of the lecture, assuming we make it there. If not, we'll do it Tuesday next week. But that we can't go the other direction. We can't always go in the other direction. Yeah. Yeah, if X increases, I don't know if Y is, Y doesn't tend to increase or decrease. I don't, so exactly, yeah. I mean, there could be some parts of X, whereas I increase there, Y tends to increase, but on average, it's defined over an expectation, right? So on average, if X increases, Y does not also increase. It stays the same on average, right? Because it's based on an expectation. Yeah.
Because the expectation you weight your one them has additional variance to it. Would that also mean like if the density was a vertical line, it would have put in the zero?
Yeah, so this is a good question, right? So what happens? The question is, you're saying covariance can be 0 if the distribution, let's say the distribution is uniform f of x, y. We have x and y is uniform over this box where x is, say, basically equals to 0.5 plus or minus maybe some little bit, and y is in so plus or minus some epsilon, and y is in 0, 1, right? So y varies a lot, but X is basically the same. This is kind of like that rectangle example back here, right? That red rectangle, that has covariance 0. If uniform distribution over that, and I've scaled and I've made the kind of, this is expected value of X, and this is the expected value of Y. Okay, the covariance here of X, Y is also equal to 0, right? So this is maybe a little bit unintuitive. It's the same, it's also the case if I have kind of a uniform box. It's also equal to 0. Yeah, so it's not, covariance does not tell you everything about the distribution, right? It's boiling it down, a joint distribution boiled down to one number, right? So it's not necessarily tells you everything about it. It just tells you how X and Y vary together, summarized in this one number. Is that? Okay, we'll see other ways of describing distributions and modeling them, but it's much more to know, say, it's a uniform distribution with some parameters. That tells you much more about the variables in still fairly compact way than just the covariance. Yeah. Well, but then I don't know how they covary with each other. They could both be uniform by themselves, but have covariance with them. Let's see, right? So I could think of another example where it's basically uniform, but over this kind of, or, I could, if I do it properly, it's kind of like this. So it's kind of uniform over here. And if I did this properly, well, X is uniform over this range and Y is uniform over this range. And I can get the variance, but I don't know that these have a very strong covariance, right? This is much greater than 0 in some sense, right? But I could also do it the other direction. I could also make it much less than 0, but the variances of X and Y are the same. Okay, so it doesn't, the variances by themselves don't tell me much about the joint variance. Those are kind of the marginalized variance. I've removed information about how it relates to the other variable. Yeah. So, okay. So I've just told you, if you've noticed, I've just talked about how covariance is either 0, greater than 0, or less than 0, but not how big should it be, right? How big is a lot of covariance? How is 0.001, is that bigger than 0? Yeah, that's bigger than 0, right? How big do I need it to be to say anything so useful? That's where correlation comes in. Okay. Okay, so correlation is going to be, we'll use rho of X and Y. Okay. This one is kind of a version of covariance that we have some notion of scale to. We know how, if something is big or if it's not big. Okay. So we do this because we don't know how big is big with covariance, right? Is 0.0001 big or not? I actually don't know. It could be a really big covariance if it's 0.001. It depends on the scale of how much variance there is, right? If the variance is even smaller than that, then, right? Like I drew these pictures, but I didn't put any values down, right? Like how big is the covariance here? Well, it depends what the scale of the x-axis is, right? If the whole scale of the x-axis is like 1/10⁻²⁰, well, then this is a very small covariance. But these are very correlated in that blue strip. Okay, so I need to somehow get a number that I can actually understand how big is big. Okay, does that make sense? Maybe. Okay, how about I define it and then hopefully and tell you some properties and you'll see why this is useful. Okay, or if I change kind of the units of stuff, right? It messes up the covariance. The correlation won't have units. So it'll not depend on the units that I measure stuff in, okay? So the correlation of X and Y is going to be equal to the covariance of X and Y, okay? But I'm gonna add something else. I'm not so done yet, okay? Otherwise that would, you probably shouldn't believe me. Okay, divided by the variance of X, divided by the variance of Y, square root. Okay, so yeah, if you remember, if X is measured in like, so if X is measured in like, so meters, and Y, I'll draw a little bit better Y here. Y is measured in, so like, so seconds. The units of, so covariance is going to be meters times seconds, which seems a little weird, right? So this is in M times S. That's the units. The variance of X. What is the variance of X? What units does the variance of X have? Squared meters, right? Yeah, so this one is in meters squared, and the variance of Y would then be, so the should be the seconds squared, okay? But then I multiply those together and take the square root, right? So the whole bottom here is square root of meters squared times seconds squared. And actually the numerator and the denominator so cancel, okay? So all those units cancel out. So the correlation does not have units, okay, which means we can actually say how big is without worrying about the units or the scale of our plots. Okay. All right. So, oh, don't have this written down, but I assume so the yeah, so the correlation XY is going to be in the range from -1 to 1. Okay, so the correlation has to be between -1 and 1. So now we know if the correlation is close to 1, that means it's really well, they covary very closely, right? And if it's very close to -1, then as X increases, Y decreases a lot. Okay, and if it's 0, it's still close to 0. But now we kind of know how big is big. If it's close to 1, it's big. If it's close to -1, it's small. And if it's far from 1 or -1 in the sense of close to 0, then we know they're not very correlated. Okay, so correlation is related to covariance, but it gives us kind of some quantity that we can understand how big some, the aspects are. Yeah. Right. I'm telling you that I don't have that written down in my notes, but if I so if I'm like 99.9% sure this is correct, but in the heat of a lecture maybe I made a mistake, but if I'm pretty confident it's true. Yeah, but the whole point is that it gives you this notion of scale, right? Could probably derive that that's the case. Yeah, in front.
Like, the correlation, and it's just the correlation of X to X. That's about as high as the correlation you get, and that's just the variance of X squared and the variance of X squared.
Great, Perfect. Thank you. Yeah, so it has to be at least, it can't be more than 1. It can't be less than -1 because as small as it can get is x and negative x. If y is negative x, you'll get exactly -1. Great, thank you. Yeah. Yeah, so how big, okay, so I told you we would be able to quantify how big is big, right? How big does it need to be for it to be big? Okay, there's still some kind of like mushy middle where where you kind of say, that's kind of big, but not so big, and it's fruitless to try and draw a line. Okay. All right. So in statistics, people really want to draw these lines, and we'll discuss more about this. And it's kind of like, you're just kind of you kind of draw some arbitrary threshold someplace. Yeah. So, but like if it's probably just bigger than 0.8, that's highly correlated. If it's less than 0.2, probably not very correlated. Less than 0.1, you might say not correlated. In the middle, you can say something else, right? But your mileage may vary. Some people may say, well, 0.1, that is some correlation. It's not zero correlation. Maybe you can use like boosting or something to kind of pick that up, right? So it all depends on your perspective, right? Okay, so great question. Okay. Okay. Here's what I'm going to do. I'm going to write down an example. I'm going to write this quickly down. The Gaussian, which is kind of the multivariate, so normal. And in this case, we'll look at a 2-variate, where this can go to d dimensions, and we'll look at 2 dimensions here. Okay, let me just write down this kind of equation, f of x, y, which turns out to be, so this is equal to, there's some normalization term, right? Normalization times this quantity. Okay, so let me write these down in 2 parts. The blue part here, expectation, is going to be, we saw the normal distribution, but now this is slightly more complicated. It depends on the, so this is going to depend on the mean of x, the mean of y, and the correlation of x and y, and the variance of x and the variance of y. That's of y. Okay. So 2 times 1 minus rho squared. Okay. Times kind of the good part in the middle. X minus, okay, x minus mu of x squared, 2 sigma x squared, right? This is what the middle of the normal distribution looked like for just x. If you have a y term, you also vary in the y, 2 sigma y squared. Okay, and then there's going to be potentially some covariance, but this might be 0. 2 times the covariance of x and y of x minus mu of x, y minus mu of x, divided by sigma x, so sigma y. Okay, so this is, so the multivariate normal distribution is going to have some normalization term. I'll just, don't need to write it up. It'll kind of look in the books. You can look up in the books. But if there's some mean, for actually, let's center it someplace not on the mean. This point is mu x, mu y. Okay, and then there are going to be these iso levels that are going to come out here. And this one has correlation. X is correlated with y, so this rho is going to be so positive. Rho is greater than 0. This tells me kind of, well, this tells me the kind of the variance, the standard deviation of x, and this distance is kind of like the standard deviation of y. Okay. Okay, so this is kind of a powerful modeling thing. This is how you write down the typical thing that these bumps like this I was kind of drawing before. That's kind of how you model them as a distribution. Okay, they kind of, you kind of model them with this exponential function. So the key parts to see here is that kind of it's got this exponential thing. So that means as the numbers get bigger, it grows really rapidly. But actually, I put a negative in front here. So as x, and that means that as x gets further away from the mean, right, this value gets bigger. And I'm multiplying by -1 so that it gets smaller, closer to 0. So I'm kind of 1 over that quantity, right? And I'm getting exponentially smaller. So it's dropping off exponentially as I get further away from the mean, right? And then this quantity here kind of tells you how fast you drop off. That's what that quantity is. We looked at this in 1 dimensions before. This is kind of a little bit what the multi-dimensional thing looks like. Combination of, frankly, my handwriting is not great and it's a lot of stuff to write down. I'm not going to write it here. It's written down perfectly in the notes. Let me take a couple minutes just to show you some plots. Actually, let me do this in R on my computer. Okay. Okay. So this is linked off the webpage. Okay, so this is the function. I've written down the function where I pass in a value x and y where I evaluate it. I set a mean value, default 0 for x and y, a standard deviation for x and y, which I set to be equal to 1 by default, and rho, which is default 0. That's the correlation. And this is the equation I basically wrote down before, right? Okay, and we're going to consider a bunch of values to plot on from between -4 and 4. Yeah. Yeah, let me see if I can do this. Okay, should be a little bit bigger here. Okay, and I've written this in our markdown, so you can kind of do this stuff by just clicking these things, right? And this is, I'm going to call this iso function. Yeah, I'm taking like the outer product. This is a trick to take the cross product of all the x and the y values. Okay, and then I can plot the contours here. Let's see if this renders well. Let me turn off this echo. That way it should plot over on the right side here. See if this works. Okay, let me type that in. Contour XY, F iso, aspect 1. See, hopefully this will plot over here. Oh, what am I doing? Let's, the extra U in there. Good. Okay, a little bit better, but you can see with if I didn't specialize the covariance, I forced it to draw the aspect ratio 1. Otherwise R will plot it to fill the screen. And so it's drawing it with these perfect concentric circles. These are the iso levels. You could see if you look close enough, you can see little levels little values where I write the height function on here, right? You can see the height function a little bit on there, okay? Another way to plot this, now let's do this with rho equals negative 0.75. And I have to define this first. Okay, now I should be able to do this. And iso. Okay, great. So now when I change the correlation to negative 0.75, I'm stretching it into the negative, into the lower right and the upper left quadrants, right? Right. Okay. You can also, there's this other plot. This isn't going to work very well on here, but let's see if I can plot this thing here. Hopefully that shows a bit better. Okay, it's you can kind of see the bumps. Okay, that's a bit better. You can kind of see this ridge running down there on the X and the Y. In this case, look at the arrows on the X and the Y, see what direction it's going. Okay, there's something I have working. Let's see if this works. There's here, let me try this one, see if I can get this working. This should pop up someplace. Oh, okay. This, okay, this uses X, which does not want to go on my external monitor. Okay, there. I can see something really cool where I can rotate this around. Maybe you'll play with it yourself. My X is not, who even knows what X is? Okay, it's something that allows me to draw a window. I can see a plot and move it around. You can probably play with this on your own. Okay, let me show you one more thing of something that is, and then we'll do the quick review for the quiz. We're going to show an example that is correlated, but not, so no, its covariance is 0, but they're not independent parameters. Okay, so I'm going to pick X from a normal distribution, and I'm going to say that Y is going to be either, is going to be either -1 times the value of X or +1 times the value of X. So I flip a coin, and Y is either going to be -1 times X or +1 times X. Okay, X is going to be centered around 0. Okay, so that's what this distribution is. Let me plot the histograms here. See if this works. The histogram should look both like normal distributions. Okay, this one is not echoing. My R is working a little bit wonky today. Okay, and now I can plot a histogram of X. Okay, so this is X, and if I do this same with Y, they both kind of look the same. It's kind of, I've discretized, chunked up a normal distribution. But if I plot them, let's do plot X, Y. X, Y, what is this going to look like? Like this. Okay, so these are, so they're not independent of each other. As X gets larger, Y is kind of, its absolute value gets larger, but its expected value stays the same. Okay, so these have, if you work out the covariance or the correlation of these random variables, it's going to be 0, but they're not independent of each other either. Okay, so this is an example where you get covariance of 0, but not so independent. Okay. All right, I have 10 minutes left to do a review for the quiz. So let me see if I can go back to that. Okay, let's do this. Okay, so review for quiz 8. And remember, if you guys are not been doing as well in the quiz as you like, I think it's a good idea to kind of think through the core things you might want to remember. So the first thing was continuous joint, so random variables, and you have a PDF, right? F of x, y. Okay, and I have these properties. The key properties from this is f of x, y is always greater or equal than 0. It is, I know that if I integrate from x equals minus infinity to infinity and y from minus infinity to infinity, a double integral here of f of x, y dy dx, then this has to be equal to 1. Okay, I'm not going to make you do any integral calculations on the quiz. Okay, this isn't a class in calculus. And then 3, if I want to take the probability that A is less than X is less than B, and C is less than Y is less than D, right? So this was the sort of things I could think of a probability for continuous random variables. I can't really evaluate at a point, but I can evaluate over a range. Well, then this would be the integral of x equals a up to b and y equals c up to d of, you guessed it, f of x, y, dy, so dx. Right, so that's equal, that's an equal sign here for this. That's how you would calculate that probability with this integral. Okay? It's kind of, we talked about, you can do conditional probabilities, you can do marginal probabilities, and those are just kind of pulling this stuff out, just like the discrete case. Okay, but you should kind of, you've replaced all the summations over stuff with integrals instead. And you know, if you know these probabilities and you remember the other rules, then you can kind of figure everything else out. Okay. The other, so review part 2. Yeah. Okay. This will all be posted online in just a matter of minutes. Is there a question on this? Okay. Okay. Review part 2. So the kind of the covariance, right? This is the first thing we talked about, the covariance of x and y. And this was, we can define this as, let me say, this is defined as the expectation of x minus expected value of x times y minus the expected value of y. Okay, and there's also another kind of simpler definition that you asked me so many interesting questions I didn't write up, and I'm saving it for here, but it's in the notes. You can also write this as it's a minus sign. Expectation of x, expectation of y. Okay, so this is an equivalent definition of it. This one might also be useful. Okay, and again, if covariance of x and y is greater than 0, then if x increases y expects to increase. Okay, that's kind of the way to think about it. If it's greater than 0, then if x increases, y expects it to increase. And the negative of that is true. If it's less than 0, then if x increases, y expects to decrease. Okay. Then you should know probably the so correlation. Okay, correlation is just the covariance of x, y divided by the variance of x, variance of y. That's a multiply. Let me make sure it's written clearly. Variance of y, and it's the square root of that. Okay? And correlation has the property that it's in -1 and 1, right? So this one, we kind of understand the scale here, right? We know it's between -1 and 1, so we know how big is big, okay? Okay, one couple of other things. Okay, independence. Okay, if x and y are independent, then we have the covariance of x and y is equal to 0, and also the correlation of x and y also is equal to 0, right? Because the numerator is the covariance. Okay, but if correlation x and y equals to 0, maybe not independent. Okay, so independence is a stronger property. Think of independence as a stronger property. You can say things if they're independent, but the covariance doesn't tell you as much. It's kind of, remember, there are a lot of things we're asking, does this say this? Does it say that? It kind of just tells you that they tend to increase together, or they tend not to, or they tend to one increase, the other decreases. That's all it's really telling us. So, okay. Great. I think if you kind of conceptualize all that stuff, you're going to be ready for the quiz, and maybe we'll review a couple of these plotting and some of these things later, but I think we're ready to start statistics on next week, Tuesday. So, so great. All right. I will see you next week. And there are copies of the homework up here, so pick up. And I'll be around in the room for a bit if you want to take the quiz in here, answer questions. Oh, if you're about to take the quiz, I realize there's a question that I might ask something that if you haven't started the quiz yet, maybe just wait like 5 minutes. I realize there's a question I have that might pop up on yours that I may not have covered. So let me go check this. Let me see if I can fix this quickly.